Okay, good afternoon, everyone. I hope you're doing great. Please just save this code somewhere that if your neighbors join HW0G, you can just help them. The thing is, yesterday, if you remember, we just started talking about the different tensor operations and the things that we deal with normally. We started talking about broadcasting as one of the possibilities. So it says that the gears of the neural network is tensor operations. What are the most common tensor operations that you normally deal with? One of them is dot product, for example. The other one is summation. And look at this one. Here, it says that this layer that we have already worked with, you remember it is something that we added as one of the hidden layers. It says that keras.layers that dense 512 neurons and activation is ReLU. Technically, when you say that neurons, you are talking about using weights and biases in the previous layers and multiplying by ReLU. What is ReLU if you want to define a formula for it? Very simple. ReLU is nothing but a max of x and 0. What does it mean? It means that imagine that we have imagine that if this is a coordination, if this is the x and y that we have, if we have any number below 0, it's going to return 0. For any other number above that, it's going to return the same value. So if x is, for instance, 1, then the return would be 1. That is what ReLU is. But we want to see how we can implement such things in environments like Python. So everyone, please think about this code. It says that assert length of x dot shape is equal to 2. What's the meaning of assert the x dot shape is equal to 2? Because it's not a trick question, it's very simple. Anybody? It's very simple. It means that x has 2 dimensions. It could be some rows and some columns. In this very example, we have 4 rows and 4 columns. So what is the number of dimensions here? 2. So here it says consider for I in range of x shape 1. Anyone can tell what is the x shape 0 and what is x shape 1 in something like this? Imagine that we have this kind of shape. We have 2 rows and 3 columns. When we say X shape 0, what is the number for it? What I mean? William, what is X dot shape 0? That's the number of rows. What's the X dot shape 1? Yes, the number of columns. Okay, so it's going to be 2 rows and 3 columns. So when we say that X and we say shape 0, we address this part, and when we say shape 1, we mean this one. Getting to this, it says that for every I in range of X dot shape 0 means that, what is the shape dot 0 for that example? Means 2. Means for line 1 and line 2. And then we say for the next one, for every J in range of shape 1 means the number of columns. Then go to every single element and find the maximum of that element and 0. Means what? Imagine that we have numbers like 3, 2, 1, -5, 0, and negative, oh, let's say positive 2, but this one is negative. Okay, it means that for the first loop, means that for the first loop, go to the first row. So now we are here. And then when we are in I equal to 0, then the next responsibility would be getting to the first J, which is 0, then the next J, which is 1, then the next J, which is 2, and the last J, which is 3. So go to every single element of them, the whole loops that we have here is just gonna go through every element. When the I equal to 0 is done, then we go to the next I and do the same thing. And in every single element that you have, check what is the maximum of that cell compared to 0. Means that if it is positive, then the max would be 10, for example. 10 and 0, the max is 10. And if it is negative, the max of -5 and 0 would be 0, right? In other words, it's exactly like a ReLU function. If the numbers are in this area, then the maximum of any negative number and 0 would be 0. So the y would be 0. And the any number after that, whatever it is, it's going to be the same value for it. Does that make sense? This is how we implement ReLU in Python. The next thing that we have is just adding to values, what do we say when we say the x dot shape is equal to 2? What does it mean? It means that we want to have a matrix that has 2 dimensions. What do we say when we say assert x dot shape is equal y dot shape? Anyone can elaborate on that? I'm talking about this one. Anyone can explain this? Jason? Mm-hmm. Let's start from them.
With assert x dot shape is equal to y dot shape. When we find true if it's true.
So how about this? What about the first one? Can you just say something about this line?
I think it could still be like the same logic. If length of x shape, if length of x is equal to 2, it would return true. And it would.
Which means that we have 2 dimensions. For instance, we could have something like 2 rows and 3 columns. We have 2 dimensions. That is for x. And what about the next thing that we have here? It says that then if x is 2 times 3, then y should be 2 times 3 as well. Right? Otherwise, raise error. Correct? And then we say that let's have the copy of x value. And then we say for every I in range of x dot shape 0, what is the x dot shape 0 here? Anyone can tell? Sorry? Means that it's going to be 0 and 1, those 2 lines. How about this one? 3 columns, which is going to be 0, 1, and 2. Does that make sense? So we say that for every single element in I, first let's just say I0, then we are gonna play with J. So it's gonna be 0 and 0, x 0 and 0 added to y 0 and 0. Does that make sense? So imagine that we have values like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, something like that. We are going to add this element, and we keep it back inside x. So 7 plus 1, it is going to make this x 8. So 2 and 8, it's going to make this one 10. 3 and 9 is going to make this one 11. So that's this line. It says that whatever we have in I and j for x, add the same location in y, add that value, and just save it back inside x. Does that make sense? Spend 2-3 minutes, just read the code. If you like, you can just run that on your Colab and just give an example, like what could be x, what could be y, just one example, and see how it works. Okay. How would the performance look like if that was the actual way of adding two values inside two matrices in Python? It would be awful. If we had similar steps that we needed to go to calculate, for instance, just adding to what we call it bitwise. Look at it. So we call it bitwise element summation. Then it would be awful. But the thing is, Python provided some libraries. It says that these operations are available as well optimized built-in NumPy functions. So you don't need to use any for loop. For loop means if you have nested for loop means exponential. Big O is n to the power of 2, which is not that much pleasant. It works super fast because it converted to a kind of linear operation. Anyway, let's just go a little bit further. We talked about broadcasting and we said broadcasting is not always possible. In some scenarios, we don't need to broadcasting. And what are those occasions? Look at this one. Imagine that we have something like 3 rows and 2 columns, and you want to add elements to similar 3 rows, 2 columns. So there is no need for broadcasting. But what if we have a situation like this? We have Y that contains just 1 row and 2 columns. Let's just see here we have 3, 2, but here we only have 2. The thing that two different references that we learned from the Python book in the previous semester, and in this reference they say we are going to, whenever we have different number of dimensions, first we are gonna pad 1 to the left of the smaller dimension. So in that case, we are going to have 1 here. Then now the number of dimensions are equal. We check if these two are similar, which they are. In the case that we have this similarity, like this one of the items should be 1. Then you can just increase that value. You can increase that into you can increase that value to 3. Means that you're going to do it something like this. Imagine that we have values here like 1, 2, 3, 4, 5, and 6. And here we have 10 and 20. Yes, you are going to have 10, 20, 10, 20, and you can just start adding the things together. But the question for you is, what if, oh no. What if instead of 1 rows, we have 2 rows here? What could happen? Pardon me? So if we have, let me just clean everything here. As Prakash said, if we have something like 2 rows, so it's going to be something like 2 rows and 2 columns here. And we have, I don't know, 1, 3, 5, 7. The problem is if you say that, okay, let's just increase the one which is smaller into the maximum. So let's convert this one to 3. You don't know what's going to happen for this inserted row. Are you going to keep the first row's values or the second row's values? Are you going to keep the maximum, the minimum, the average, or what? So because we don't know anything about that, we have ambiguity or it is vague. So we just do not use broadcasting for such cases. By saying that, okay, in terms of implementation, guys, if it was the case that we needed to follow for implementing, it means that actually we needed to increase the size of the memory. That was horrible. Why? Because imagine, let me just bring it back to, imagine that we had 2 columns, 1 row, and we wanted to add these 2. If you actually needed to occupy memory for it, it would be awful. We are not talking about 2 times 3. We are not talking about 3 rows, 2 columns. We are talking about hundreds of thousands of matrices that we might need. So what is the actual solution for broadcasting? Please go to page 10. First thing first, if there is no need for broadcasting, that's the simplest version. And I strongly recommend that. This was not a complete example, so I have provided something here so you can just use that. It says if the number of dimensions are equal to 1 for x and y, and the shapes are similar, like both of them have 5 elements, then simply just say multiply every single element. In this example, it's something like here. It says that multiply every single element. For instance, I is equal to 0. So multiply x 0, y 0, plus x1, y1. So it's going to be 10, 40, plus and x2, y2 is going to be 90. In general, it's going to be 140. So you're going to place that inside Z, and you're going to return that Z. This is pretty much what it wanted to say for multiplying 2 matrices. Does that make sense? Okay. By saying that, the real challenge starts in this example. It needs to refresh a little bit of our memory. So what if we want to multiply something like this? I'm going to first ask you to see how much we remember. So look at this one. Imagine that we have 2 rows and 4 columns. This is our X. 2 rows and 4 columns. What could be the Y that we can just start multiplying? Anyone?
I didn't really see all mine.
No, oh yeah, good answer. I'm talking about the vector. A vector, yeah. So means that we just have one dimension here. So should it be 2 or 4? It's either. Now imagine that we are talking about just one vector. Pardon me? What is the second dimension of X? 4. So this guy should have 4 as well, right? So look at this one. Let me just show you before I get any further. Look at this example. For multiplying a matrix and a vector, first you have to check if the length of X is 2, because we want to multiply a matrix and a vector. Let me just get a screenshot from this one and bring it. A whiteboard. So it says that first, check that the dimension for X is 2. It's a matrix. And the dimension for Y is 1, which is what? Which is a vector. Then the second thing that we have to check is the number of columns in X is equal to number of rows in Y. Does that make sense? Nash, do you think it is correct? Here we say the number of columns here is equal to what? Is equal to number of rows in here. Isn't it familiar? We are going to just multiply these two. Let me just. And then we are going to multiply these two. And then we are going to multiply these two. And then we're going to multiply these two. And what is this? This is when I is equal to 0, right? And J, it's going to create the very first element of the result. The overall is going to place in here. And then we do the same thing for the second row, and the result would come to this place. Just for a few seconds, just look at this picture. And this is a kind of very specific form of this that I provided for you. I copied it before to save our time. Yeah, there we go. Imagine that if we have just only this part, you know what's going to happen? This guy is going to multiply. This guy is going to multiply here. The same applies to this is going to multiply plus this guy is going to multiply here. Does that make sense? Yeah. So all of them are going to just create, for instance, here, just one value in here. Please, first, Try to have one example for this one. This is going to be a matrix multiply a vector. Please try to just work on that. And after that, we are going to go to the generalized format, which is going to be in this page. So first thing, spend just a few minutes. I had that experience in the previous class, so I just explained, and I didn't see that people grab it unless that you start, having example for yourself. You cannot have good understanding of that. So let's spend a few minutes on this. Okay, Al, can I have your attention, please? Look at this one. I hope I had enough time to just think about it a little. In the first part, we say, again, quickly, I go through it. We say that the number of dimensions should be 2 for this one, and the number of dimensions for y should be 1. One thing, it doesn't matter if you write the y in a kind of vertical form or horizontal form, just for the sake of imagining the shape easier, I just made it that way. So let's just consider if we have something like 2 rows for X and 4 columns. And let's just assign values like 1, 2, 3, 4, 5, 6, 7, and 8. So what is the dimension here? It is 2 rows and 4 columns. It says that the dimension for Y should be 1, means a vector. And it says that the second Y's number of elements should be equal to the shape of the second element of Y, means 4. Means we need to have something like this. 1, 2, 3, and 4. So imagine that we have 1, 2, 1, 2 as the elements. What we actually do, that's something that I wanted you to spend a few minutes and see if you can discover. So it says that, hey, for Z, we are going to 0. We are going to fill a matrix or a vector full of zeros. The shape of that should be equal to the shape of the first element of X. What is the first element of X, Rachel? It's 2. So yeah, that X dot shape 0 means that create for me a vector that has 2 elements in this example. Does that make sense? So we say that what is happening in here? I say go from I equal to 0 all the way to shape equal to 2, means that I would be first equal to 0, and then it's going to be equal to 1. Keep that. And then J would be what? Would be 0, 1, 2, and 3, but not 4. It's going to be J. What we actually do is we are going to say for I and J element, first 0 and 0, multiplied by what is J? Guys, what is J in this step? That's excellent. Pardon me? Yes. It's going to be 1 multiply 1. That's here for I 0, J 0, and J, which is going to be this one. So it's going to be 1. Keep that somewhere. And then plus, what is the, then we are going to go to the next J. What is the next J? 1. Let me just change the color. It's going to be J equal to 1. And we are multiplying by the second element. What's the value of that? 5. And then J is going to be index number 2, the third element, index number 2 here. So multiplying those two, which is going to be 3. And then the last one, J is going to be 3, the fourth element. And J is going to be 3 plus 8. Does that make sense? And what is the output? 17. So 17 would be the first element or the index I, which is 0. Then we are going to do exactly the same thing for I equal to 1 is the second row. We are going to multiply this one by this one by this one by this one by the last one, and we are going to sum them up and add them into this cell. Okay? By saying that, we just calculate this part when we have a matrix multiplying by a vector. What about when we have two matrices multiplying? Okay. This is the question. Please try to run a code for it. Here is the question. Imagine that you want to implement something for this problem. It's not that difficult. Whenever you're done, please let me know.
Can you check the recording and do you see this?
So now you can be able to see. Thank you. Okay. What's the answer? Okay, guys, how about this? Can I have your attention? Those who are in the class, I'm gonna give one. I just want to make sure that who wants to pay attention, because let's just, those who want to leave, I'm gonna give one and leave easily. If that is that's the reason that people are here. And it is recording. I'm not just saying it. It is recording. I know what I'm saying. So guys, those who are here, I hope that they want to follow up and see what is happening. And I'm sure that if the intention is just knowing at least the cutoff of the things that we need to know as people who pass this course, is these kind of things. And it is a super simple, just you need to write 2 nested loops. And even if you don't want to do that, you could just scroll down and see the answer. Just copy and paste the answer. Page number 41, it tells us what is happening here. I'm going to just copy paste this. The first thing that happens here is it tells that the number of dimensions in X should be 2. The number of dimensions in Y should be 2 as well. The last thing is the basic formula that we remember from the algebra. It says that the second dimension means, in this example, the number of columns here should be equal to the number of rows of Y. Means what? Means imagine that we have, both of them should be 2-dimensional. Imagine that we have X, something like 2 rows and 3 columns. Definitely, Y should have 3 rows and imagine that 3 columns, something like this. And the output, if I say 4 columns, you're not going to get confused. So 4 columns. And the output would be 2 rows and 4 columns. But how we calculate this? Very simple. We are going to start from I equal to 0. J is going to be equal to, that is the J value. J is going to iterate. So this guy is going to multiply this one. The next one, this one is going to multiply this one. And the next one, this one is going to multiply this one. Technically, it is pretty close to what I have provided in top of the page for you. In here, or this is just for the first element. You multiply A1, B1, A2, B4, A3, B7, and it's going to shape you the first element, which is going to be row number 0, column number 0. And the multiplication of this row, Mikita, what do you think? This row and this row, what's gonna stay? So we're gonna multiply this, this, and this. What's gonna be the position? Tell me about the C2, C3, C4. What is the position of that? Yes? Okay, let's ease the job. What is this one? I is equal to 1 in this and this one, right? What is the, tell me, what is the column that we have here? Column 0. So it's gonna be 1 and 0. What is the element 1? It's going to be here. What is the element column 0? It's going to be. Does that make sense? Don't worry. Now you're gonna remember forever. If you just get yourself into a discussion. So how about this one? Imagine that this one, I want to multiply it by this. What would be the position of these two? Yes, I could. Okay, why C8? Would you please tell me? Okay, this is 0, 1, 2. So it's gonna be 2, comma. What is the column number here? Column 1. So it's gonna be row number 2, column number 1. Row number 0, 1, 2, and column 0, 1. It's going to be this one as Atakan writes, right? Atakan said. Yeah. So if you look at the, let me just bring a little bit white space and say Control V. Yeah. If you see here, we have I rows, J column, and we multiply, we say, hey, for every single element that we have in row, multiply it to every single element that we have in the column. To understand it better, they provided this one. Just give me a second to. when you read the book, means that, for instance, these two have, I don't know, 10 numbers. The first element in the row, you have to multiply it by the first element in this column, and you go all the way down, you add them all together, and it's going to shape Z element for you. Okay. The reshaping is the first thing that we learned when we worked with NumPy. Everybody, please go to the Colab, the file that I've provided for you. I knew that it was very tough to type the code, so the code is already typed. You just need to run the code. I think for the next series that I teach, I have to run the code as well. If you go to the Colab, the last 12 commands, the first one is going to be this one. It says that imports NumPy, and then we say, let's have 3 rows and 2 columns. We run those two. So now we have 3 rows, 2 columns, means 6 elements. You can reshape it to any format that contains 6 elements. Means it could be 6 rows, 1 column. It could be 1 row, 6 columns. So it's going to be reshaped like that. And the next element is 2 rows, 3 columns. And so on. Did you finish running it? Do you know where to find that, Daniel? This file? You don't know where to find? Please go to the course content, the last file over there. The course content, chapter 2, MNIST version 2. Download it, bring it to Colab. It's going to bring you there. Done? Okay. Let's see what transpose is. Look at this one. If I say I have values like, I'm going to enter some values randomly, like 1, 2, 3, 4, and then 5, 6, 7. I'm sorry. 5, 6, 7, 8. If I say Control C in Excel and I bring it somewhere else and say right click and then transpose, look, we have 4 rows, 2 columns. It's going to make it 2 rows, 4 columns. So it's going to be 1, 2, 3, 4, something like this. So if you just go to that transpose. For instance, if you say I want to have zeros, 300 rows and 20 columns, and I want to transpose, and if you check the shape, it's going to be now 220 rows and 300 columns, right? You saw the sample. One of the things that it mentioned that I very much like, it is like, give me a second that I can just show you an example here. Okay. Imagine that we have something like this, right? What do we normally do in deep learning? If we have something like A0 for here, A1 for here, and A2 for here, this line, this line, this line, these are weights. So it's going to be W0, W1, and W2. You multiply these, you're going to say A0, W0 plus A1, W1 plus A2, W2. If you want to write it in a kind of nicely math format, it's going to be AIWI sigma I is equal to 0 all the way to n. And then we have something on top of this guy, which we call it bias. So this one is going to be plus b. And the whole thing is going to be multiplied by a function that we call it ReLU. What is this in general? If A is something, yes, that's going to be the output of this, which is going to be the first hidden layers neuron, right? For that one. We do the same thing for here. Thank you. We do the same thing for here, do the same thing for here. So technically this, what is this one in general format? It's nothing but, for instance, if we have A somewhere here, imagine that this is A. As James said, imagine that we want to get to an output here, which is going to be B, right? We get from A to B. Am I right? With transposing, with saying all those multiplication and summation and so on, we get from one place to another, isn't it? So, okay, is it possible to say after that for the next layer, we go from B to somewhere like C? After that, we go to somewhere like D. These are the things that we do, passing every single layer. In that case, what's going to happen? We transform the data that we have in layer to another data. That transformation is like a geometrical transformation that we learned in algebra. We just move one value to next layer, next layer, next layer. It's like filtering, changing the values to get closer to the data. Look at this one. It says that neural networks consist entirely of chains of tensor operations, and that all of these tensor operations are just geometric transformation of the input data. it follows it follows that you can, interpret a neural network as a very complex geometric transformation in a high dimensional space implemented via a long series of simple steps. It says that it's like you have already a crumpled set of papers, and you just decrumple them in every single move. It says incrementally decomposing a complicated geometric transformation into a long chain of elementary ones is what we do actually in deep learning. For what reason? To get a picture simply and tell you that if it is a cat or dog, if it is 0, 1, 2, 3, or what. So by saying that, we get to a new chapter, and that is about neural networks, gradient-based optimization. So I'm going to pause it here for now. Let me ask you one thing. How many of you remember exactly what we had in derivatives and gradient descent high school? How to calculate derivatives? Anyone remembers? Barely remember. Okay, the good thing is we have a nice prof here. No, I'm not talking about me. I'm talking about this nice prof. I bet you wish you had this prof instead of me, who nags all the time. Let me just. And she actually teaches very advanced math. Okay, there we go. Control C. Jason, can you please double check actually, that if you can see. Okay, so you can hear that, right?
Long story short, it's a function that tells you the slope of the line tangent curve.
Okay, so let's pause everything here. Let's have something like 15 minutes. I need to do something during the break that I promised. Sorry. I'm gonna pause the recording. So let's have 15 minutes or something. If I come a little bit with 2-3 minutes delay, my apologies, but I'm gonna try my best to be here in 15 minutes.
Yeah.
Shows that still. Okay, so what we are gonna do, and you can see this one, right? Okay, let's just watch for a few minutes.
At any point. It gives you the rate of change at any instant, instantaneous rate of change at any point. And we're going to figure out the proper definition of the derivative of the limits. But you just can't wait to use it to calculate the derivative. Skip ahead and jump to time discussion. Or you can go down this round with us. But say you have a curve, a random curve. The derivative tells you the slope at any point on your curve. The steepness or rise of the moon is slope. But really, what it's telling you is the slope of the line tangent. Tangent line is a line that touches at only one point of the curve. It skims the surface, grazes the curve, and touches at only one point. And every point on your graph has a different little tangent line. So if the derivative is supposed to tell you the slope at each little tangent line, how can we know that slope if we only know one point for sure on each tangent line, and you know we need 2 points to find the slope?
Because did you get that? To know the slope, how many points we need to have? Well, definitely you need to have 2 points to just draw a line. Am I right? Well, the thing is, even in that case, you need to have 2 points to say this is horizontal and this is vertical. Because you just have 1 point. Which direction you want to go? This way or that way? You should say, okay, go towards this point, right? Technically, you have 2 points. But the problem is, in every single part in here, in every single part in this graph, we just have 1 point. So what is the slope? How can we understand the slope? Listen to this part.
You don't know how to do that yet. I mean, if we had instead a straight line graph, a linear function, like that, we would know the slope everywhere. Because if any 2 points there, use the slope formula, get a number for slope, and it would be the same everywhere. So you'd be done. But life is not that simple. Usually, our graph is curved and the slope is changing everywhere. It's different everywhere. So how can we know the slope everywhere? If it's always changing and we only know 1 point for sure on each tangent plane. Like I said, we don't know how to do that yet. We are not that sophisticated yet, but we can figure it out from things that we do know. And we can make the actual definition of formula. The further derivative, if we want to know the slope of this tangent line at any point, call it x, we can start with what we do know, the good old slope of a straight line between 2 points, pick a second point somewhere on the curve, and draw a straight line through. And we know how to find the slope of a straight line with the old-fashioned slope formula, which is a throwback to middle school probably. So finding the slope between 2 points has come back to haunt you. But you have to know your points, so let's label them. If the second point is some distance away horizontally, let's call that distance h. Then this point has an x coordinate that is h more than x, or x plus h. We want the actual points, the xy pairs. So for this point, for the xy pair, the x coordinate will be x. And the y coordinate we'll call f of x, which just stands for the y-value function you give us. So that's that point. And for this other point, for the xy pair, the x coordinate will be not x, but x plus h. And y coordinate will be not f of x, but f of x plus h. Just hear me, this is all going somewhere. We have 2 points, which is great because we can use those 2 points in the slope formula that we know and love. slope formula is the rise over run, or vertical change over the horizontal change. It's the second y minus the first y all over the second x minus the first x. So let's use that for our 2 points. Okay, so this is the slope that we found for the secant line. I just simplify and cancel x's at the bottom, but this is the slope, and it ended up being the difference in the y's over the horizontal difference in h. So the slope of the secant line, and it's also known as the difference quotient. If you hear that, you guys need to quotient of differences, very original name. This is the slope of the secant line. We are halfway to the derivative, so bear with me. We are almost to the derivative, and we would be there, we'd be done if we had a straight like that, a linear function. Slope we found would be right everywhere, would be enough. We don't have that, we have a curved graph. And the straight line secant slope that we found, it's actually an okay approximation for the slope. That point x, it's a rough estimate, and that's a big part of calculus, is estimating something non-linear with something linear. So it's a rough estimate, the slope we found, and it's not great, but it's decent. Let's not settle for decent. We don't want an approximation of the slope here. We want the exact slope, the real slope there, and not some wonky approximation between it and some point nearby. Now, we can make it exact if we close in on x by narrowing h to 0 and picking a right point that is closer and closer to the left, so that the horizontal distance gets smaller and smaller. And the closer those 2 points are together, the more accurate our estimate is for the slope at that point. And we can make it perfect if we make h so small, make h infinitely smaller by taking the limits as h approaches 0.
That's the definition of derivative. If the h is super small, then we are going to have two very much close points that we can just draw a line. So it's not going to be one line. It's going to be 2 points, right? It's not going to be 1 point. It's going to be 2 points that are very close.
So we're gonna do a better and better approximation until it's so the secant line becomes the tangent line. As this point shifts toward x, by the time it's the same point as x, this line is accurate, the tangent line slope. So the secant line becomes the tangent line. The slope of the secant line becomes the slope of the tangent line. In other words, the limit of the secant slope is the tangent line slope, but it's only touching at 1 point. And so this limit is the slope of the tangent line. And surprise, surprise, that limit also defines the derivative. This is the definition of the derivative. So we have finally arrived at the definition of the derivative.
Okay, that's pretty much what we know to proceed. But look at this part. Quickly tell me. What is the slope here? Is it positive or negative? Positive, right? How about this one? How about this one? Imagine that this is like this. Okay. What is the relationship between weights and loss. Technically, we can say losses are functions based on weights, right? So you have f of w that creates losses for you. True or false? Think about it. You change w's, it's going to increase. You change weights, it's going to increase or decrease the loss. Technically, changing weights is going to end up changing loss for you. What is the goal for that, Nicholas? The goal is minimizing the loss or maximizing the loss? Pardon? Maximizing the loss? Do we want to have maximizing error? So, okay, so here we are going to have loss and we want to minimize the loss, minimize the error. Means we want to get to this part or this part. If I call this one 1 and this one 2, which one is ideal for us? 1 or 2?
Because you can pick any two.
Imagine that we have point 1 here. This, I show it with this one 1 and this one 2. Which one is ideal for us in general? Yes. Why 2? There is no wrong answer, by the way. Thanks for participation, but why 2? Okay, so imagine that here we have x, or in this example, this one is going to be w, and in the other axis, we have what? We have y, which is f of w, and it provides loss for us. Okay, which one is lower? This one or this one? 1 or 2. So you see that 1 has a lower value for loss, right? Yes, this is minimal, but it is local minimal. How about this? This is global minimum. And our aim should be reaching this one to getting the global minimum, right? But it's not easy. Who's responsible to find the best minimal loss? Loss function is responsible to calculate the loss, but who's responsible to optimize the model and reduce the loss? Exactly, optimize. Do you read the book? You can see that even kind of is very much. Okay, let's just get a little bit further in the book and see what we are looking for. It talks about just, I mean, some math like when you say fx plus epsilon of x, you can just say it's equal to y plus epsilon of y, and epsilon of y could be something like a multiply epsilon of x, but forget about all this. You already said that this is the slope, this one is negative, right? means that the more that you go towards right, the less you're gonna get, right? It's gonna be downhill kind of thing. I want to ask you one thing. This is what I told you. So what we have as the Y predict, we have two things. We have what we call it Y predict, and we have the actual label that we call it Y. And the difference between these two is delta or L loss, right? So imagine that you have hundreds of thousands of those weights in the network. Look at this one. How are you going to calculate the loss for something like this? Imagine that you have a picture here, and that picture is a picture of a cat. And this guy says, hey, it's 20% cat, 80% dog, right? What is the loss in here? 80% loss, right? Okay, how you're gonna fix this? You know that at the beginning, all these weights and biases are randomness and all biases zeros.
Which weight is more like on the basis of which weight is more dependent.
Okay, look at this one, please. Let me give you quickly the proper. It says that a gradient is the derivative of a tensor operation. And then it says it's the generalization of the concept of derivatives to function of multidimensional inputs. But why we need such a thing? It gives you a very decent example. Just give me a second. I want to find that. Yes, there we go. Right. Everything that I told you here in next 10, 20 minutes, it's gonna explain everything that we have learned. And it's gonna explain why we use this architecture the way that we have used it in almost in all neural networks that we have. Look at this one. It says everything is something like this dot some products that dot and some that we already learned. Everything that you can change, everything that you can change by yourself, like the number of neurons, like the number of hidden layers, like the number of epochs, like the number of batch, we call them hyperparameters. If you want, write it somewhere. Hyperparameters are the things that you are able to change it by yourself. But there are some variables that you cannot change them by yourself. Like what? Like the values for weights and biases. We call them parameters. So parameters are the things that computer, deep neural nets, are responsible to calculate. Hyperparameters are those that we are responsible. Does that make sense? Okay, look at this one. It says that initially these weight matrices are filled with small random values. We know that. So at the beginning, we shouldn't expect that it's going to provide any miracle and any phenomena answer. So how we are gonna just fix our errors? Look at this one. It says that at the beginning we have lots of off answers, but the gradual adjustments. So we are gonna gradually make it better and better. We don't know how, but let's just say we are gonna make it better and better. This gradual adjustment, also called what? Training. So training is the process of correcting your errors by yourself. Does that make sense? So you have some problems, you're gonna fix them. We call it learning. And it says that it's basically the learning that machine learning is all about. How that happens, you just go through one epoch. You say that at the beginning, random values for weights and biases are this. Instead of saying cat, it says dog. And then you start tweaking those weights and biases. Now we get to the main question. How we are gonna do that? Guys, if we look at this, and which is a toy example, we have good number of weights and 3 biases. What is your suggestion? Nash, if I just say, hey, I'm going to make everything fixed. I'm sorry, it shouldn't be like that. It should be exactly like this. Where is the head of? Anyway, it's going to be exactly like this, except this weight, except this one. I'm going to freeze the whole network, guys, the whole network. I'm gonna freeze everything and just start changing that value. Imagine the weight that we have here. This could be an actual example. Imagine that vector that I have there, that weight is right now 0.3. And the loss score that I have, guys, just let's fabricate. It is something like 0.7. Huge loss. Okay. I'm gonna say, you know what? I'm going to increase that value to 35. And then I calculate, it's better to say, recalculate the loss. And the loss is going to be 0.8. Guys, was it a good move or bad move? Bad move, because we increased the error, right? So what if I say, okay, instead of that, I'm going to say 25. And then the result would be something like 0.5 compared to what it was before. So guys, it's a good move or bad move? Okay, it's a good move, right? So we understand that if we go to increment the value of weight, it's going to impact positively on our result, accuracy of our result. Does that make sense? Yeah. Okay. What if I just keep continuous? For instance, I continue and say 0.2 and it goes to 3, then still we can just say good move. But what if I just decrease again? And in that case, it says, okay, it's 45. Then I understand that it should be something between these two values, right? Guys, are you getting closer to what is happening? But the problem starts from this point. First, this is super expensive approach. First thing first, the question is it doable? Yes or no? Even this crappy basic approach, is it doable? I'm not saying that is it high in performance or is it efficient? I'm asking, is it doable? Yes, guys, listen to this part. I had a prof, he was my supervisor. He said a very good thing. He said, why we once in a while we change the protocols for security, because with the reasonable amount of time, and reasonable resources, we cannot break the code. But after improvement in the hardware and algorithms, then that time is going to reduce. So then you need to raise the bar. Exactly about this one, I'm saying if you have enough resources and enough time, yes, you can rely on that. But this is not efficient. How we can make it efficient? And there is another problem. Nobody addressed that. Listen, this good is just the good of this specific weight, but not necessarily overall good. Because when you change this, it's going to impact on all of these guys. How you could be sure that if you change this one, it's going to positively impact on the rest? It's not like an island independent from the others. It is in touch with the others. That's the second problem. So first, inefficient. It's not efficient. Second, we don't know if a local good value is a global good value as well. Does that make sense? So we need something efficient. What do you think it could be? And we just learned about derivatives, right? Look at this one. The good thing is you can do it simultaneously for all weights at once. You can simply say, hey, you know what? Calculate the derivative of this one for me, calculate the derivative of the next one for me, and so on and so forth. So if you look, we have that ability. You're going to simultaneously calculate a derivative of this, a derivative of that, and so on, and so on, right? And that random W that we have, is going to show, for instance, we have something like this. The slope is going to be something like this here. The slope is going to be something like this here, right? So imagine that our random W is here, a random W is here, a random W is here. Everybody could follow, guys. Imagine that I have to draw that for every single weights that I have. I just pick a few. Everybody could follow so far? Sure. Do you see this line? This is weight. That's not the best weight. All right. So this weight, if I just change it, it's going to impact on the loss. William, is it clear so far? The change of the weight is going to change of the loss. So there's a kind of relationship. There's a kind of, and that relationship is like F of W is our loss, right? Loss. True. And it changes the loss whenever you change this. The good thing is we can calculate that F of W. And the idea of that is to look for all of them. The idea is getting to this point. And intentionally, I just show you a simplified version. What do you mean by that, Reza? Simplified version. What about this one? What would be the ideal? 1 or 2, guys? Tell me, please. Definitely 2. We want to have lower F of W. Yes, please.
You're showing like these lines across the slope. How do you you're picking ones that are going down and picking ones that are going up?
Lovely. Okay, just one thing, because I want to focus on Stefan's question now. Is everything clear now for you by this picture? Means that the relationship between weights and the loss is something like a function. Is it clear? It could be, what does it mean? That's a good question that I received from one of our team members. Said that, Reza, what do you mean by there is a function? Means that Imagine I have just one machine that I change the value of W and it's going to increase the loss or decrease the loss. This graph just tells us that, nothing more. Does that make sense? Listen to me. If I say this means what? Means that I increase the W and it is going to, in this point, it is going to increase the loss and then it's going to decrease the loss. That's the kind of local minimum. Then again, a little bit increase, decrease, global minima, and increase. Everything is clear so far? Yeah. But now getting to Stefan's question. What do you mean? Do you accept that? And guys, if you understand Stefan's question, you understand the whole loss and relationship between. Look, these are the values. My apologies. Wait a second. These are the values of what? W. These are the values of what? Loss based on W's, right? And we said when we initialize a model, it's going to pick calculated or random weights. Tell me, random weights. So it's going to be this point, for example. And for, I'm sorry. And for that point, please tell me, what is the derivative? It's that line. Is it okay? Now I'm going to just connect the dots in a few seconds, but do you accept? Okay. So we have a derivative. Tell me, that derivatives tell us one thing. Is it positive or negative? It's positive, right? Means that if you add the value of W, guys, those whose algebra is like Reza, please pay attention to this part. We just need this. We don't need very much. If we add a little bit like W0 into it, a little bit, is it going to get better or worse? Imagine this is positive. If I go towards positive, is it going to get better or worse? Lovely, you got the answer. That's what we need to do. Optimizer is there to do that. Finish. Optimizer is there to say, hey, I found it. The slope is positive. Then go back, paddle back. Go opposite. Does that make sense? Means I need to go towards this. And we think that, okay, it's a solved problem now, but it is not. Look at the problems that we could have. What if I go slowly, 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 and slowly? Guys, what's going to happen? Tell me. Honestly, I'm sorry, just to confess, in the morning, I didn't feel good at all, and I'm under medication. It was one of the worst presentations that I had. But I'm telling you, this that I'm telling you now is one of the best. Because now the painkiller started working. And honestly, I can understand what I'm saying. Just please be with me. And I guarantee 100% that after 30 minutes, you can just relate to every single thing that we learned so far will make sense. So please be with me. If it is going to be small steps like that, next year, this time, you're gonna come to school and see still it is working and no results. So the problem of the small steps. What if, just a second, what if I use a big step like, oh, not that. What if I use a big step like this? Guys, then it was positive, now it is negative. Uh-oh. You see that? The other problem, if I don't have proper steps, look at this one. It goes from here, 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 here. Yay, I'm the happiest person in the world because it is the minimum value. But the problem is it is local minimum. Do you see that? It's like you have a tennis ball here. And you just throw it, but slowly. This guy goes like this, like this. Got there, stuck there. Look at the threads that we have here. If you do not have proper step, you can get trapped inside local minimum values. If you make it super big, then you are gonna pass the global minimal that you could have, and you never can, just because it is super big. Guys, in a group of 2, 3, just think, because I'm going to give you the answer, but just think and share what could be the best answer, what could be the best approach. For finding the global minimum. Any idea? Yes.
That big, but big step instead of going with a small step. Most probably you will not gonna find the like best case, but you will find the nearest of the best. It would be
Okay, I like the answer. But let's be more specific. He wants to write an algorithm because now you have the idea. And those are the ideas need to change into quantities. What do you mean by not that big? Yes, sir.
Try to adjust the weights and
Adjust.
the way where we have the negative loss score and the positive loss score, and then I would start changing the weights between those 2 points to find the global minimum.
Okay. Thank you very much. Let me ask you one thing, getting back to this picture before Stefan's question. Guys, do you believe that in these pictures we know if the slope is positive or negative, right? And we got the strategy, if it is positive, go towards negative. If it is negative, go towards positive. If we have here, the value is in here, right? It is negative, am I right? Then go towards positive. So it's going to be, the next is going to be like this, the next is going to be like this, the next is going to be like this. I'm talking about ideal. If you know which direction and which, the problem is the step size now. Guys, did you get the problem before was we needed to freeze all the other weights and biases. Right now, thanks to derivative, we know that, okay, we can control everything at the moment. We see that we have lots of lines, guys. Just imagine what I see. Imagine in front of you, you have something like this. All the rows, all the weights and biases, they have those graphs. And you have already positive, negative stops. You know, okay, for that one, we should go to positive because it is negative stop. For that one, we should do this. For that one, we should do this. Now the problem is limited. But the question for now is the step size. Am I right? How about this algorithm that I tell you? Look, yes.
They all have their own graphs. When we overlap them, wouldn't they have a same common point of loss?
Oh, no, the loss could be different in that.
And when we overlap the slopes and the graph like the left,
Uh-huh.
they would be a common point, right? For sure, they would be a common point because we are working with weights and they will sure be like at least a small difference like between 0.0 something, but there will be a overlapping between the graphs and wouldn't that be the global minimum where which is what we're trying to find?
We are talking about, okay, that's a good thing. We are talking about that weight separate from the other weight, separate from the other weight. We are talking about them separately. This is how we are gonna picture it. And I'm gonna tell you later what is the actual implementation. But for now, let's imagine that they are separate. And we want to find the best for one, the best for the other, the best for the other. Okay, so look at this one. Just, it's gonna cover part of the answer that you want. Imagine that we have, guys, this is the answer. Imagine that, I'm sorry, this is the graph that we have. I'm talking about a lucky case. W is in here, right? W is in here. And I take one step, and that step is this big. What is the slope here? Positive. I know that I should go towards negative, right? And I use this h size for the step. Then guys, tell me, what is the slope now? Negative. Reza, you know what? It was a big step. Half the size, which is going to be this amount, and go towards positive now because the slope is negative. Now the next point would be here, right? Still it is big, and it's going to just be what? Positive. Now we have to go towards negative. So again, half the size of that means that this amount go towards this, right? Not that bad. We are getting closer to that. So keep moving that size. Now we are this, half the size of that. Whenever we have change in the sign, then just half the steps to opposite, half the steps to opposite, half the steps to opposite. Does that make sense? And it's going to find, and this is just one algorithm that they use. And what you said at the beginning, that not that big, it is exactly what they do. They have a kind of general idea. That is why that they don't start from a thin air. So Ram's prop is better than Adam because it starts with the step, which is not that big, but big enough to find a global minimum. Adam is good to find local. So did you get the idea how to find the derivative, how to just correct itself? Yes or no? Rachel, did you get the general idea? I said we have this one, which is positive, and we have this one, which is negative, right? So we just have to step, correct myself. If it is again changing the sign, just have to step. If not changing the sign, keep moving till the time that you change the sign again. And you're gonna just make it smaller, 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 which is acceptable. Okay? Now the question, is it the best to have zero loss for all of these values, yes or no? Guys, imagine that we have those kind of, have you seen those, what do we call it in English? Pendle or pendles? Those kind of pendulum, right? Okay, yes. So the pendulum that you see, that imagine that they are separately, they just move and they just lose their power and then they just start. And finally, they're going to be all zeros. Do you think that that's the ideal case? Prakash, when we say 30 epochs, it's like make those pendulum like this for all of them. Zero loss, 100% accuracy. Is this the best? Yes, it is the best for data in hand. But what about a new picture? It's not going to show zero. So guys, could you connect now the dots? Didn't I promise that, guys? Just wait. And in less than half an hour, I just connect all the dots. So now we know, first, next week, with saying all this, I'm gonna bring you to this familiar story. Everything started from this picture. But now when you look at it, you know almost everything about it. You know the weights, you know the biases, you know how they start, how they correct themselves. Are they gonna do it separately, independently? Are they gonna do it in conjunction, in relationship with the others? What are the parameters that we have to control, like number of neurons, number of layers, number of epochs, number of batch sizes? So we have two mini batch, we have full batch, we have individual. So which one is the fastest? Which one is the most accurate? These are the things that we are gonna discuss further, but I hope that everybody could follow what I said so far. So let's go a bit together in the book. There are four phases that we have obvious. First, we want to pick a batch of pictures and say that these are the pictures, these are the labels, and run the network to say, okay, calculate Y predict for me. That's the second phase. The third phase is after calculating after predicting Y prime, we calculate the loss value. Till this moment, these three steps are super easy. The real problem is this part. Phase 4, we say update, I'm sorry. We say update all weights of the network in a way that slightly reduces the loss on this batch. Imagine that still we don't know anything about derivatives. So it says that the difficult part is step 4, how to update the values of weights in an efficient way. One naive solution would be freezing all. Do you remember that I said, let's just freeze all and just change one? The problem was not efficient. Second problem, if one is good, it's not necessarily the good in general. It's good just that. Does that make sense? This is the example that we talked. Imagine that the weight is 0.3, and if you change and it shows you 0.5 error loss. If you increase it and it exacerbates the situation, the loss, then you go the other way and it's going to show you that apparently it's going to get better. But this approach, freezing, is going to be horrible because it's inefficient, and we use the derivative. We already learned that, and we want to go to something like there. Look at this. It says that the derivative completely describe how fx evolves as you change the x. Here you can just say how error loss evolves as you change the weight. You can read it that way. So gradient is the derivative of a tensor operation. It is the generalization of the concept of derivatives of function of multidimensional inputs. It says finally, just you need this part. I already told you the loss is equal to f of w. So if the data inputs and y are frozen, then this can be interpreted as a function mapping values of w to loss values. If we go further, it says that instead of step 4, let's break it down to 2 steps. We say that compute the gradient of loss. You remember it was like find the loss function in the last. we say that compute the gradient of loss with regard to the network's parameters. What are the network parameters, guys? I said it. We have hyperparameters, we have parameters. What are the parameters? Weights and biases. So, and then we say, move the parameters a little in the opposite direction from the gradient. For example, W is, did you get this one that it says? Opposite of the gradient means if it is positive slope, just go towards negative. If it is negative, go towards positive. The meaning of that is this. The other thing, it talks about the mini batch stochastic gradient because it says if you go to the two sides of the extreme, if you just check one picture at a time, or if you check 60,000 pictures at a time, they are kind of two sides of the extreme to calculate the loss. The best is to pick something like 100, 128. We call that batch size, mini batch. Do you see the steps that we have here? One, we had a prof, let me just say, the efficient compromise between two extremes, guys. It talks about batch equal to 1, batch equal to overall number of samples is mini batch. Is to use mini batch of reasonable size. Every weight coefficient in a neural network is a free dimension in the space. Do you see this? We just, instead of having one W, we just said, what if it is two-dimensional? Please tell me, in something like this, how many dimensions do we have? 1 or 2? Or 3? 3. I have a bad news. We have n dimensions. It's not 1, it's not 2, it's not. As long as we have weights, it's like, because all of them are changing at the same time relevant to the others. We have n dimension. You see that, William? Here we have n connections, n number of weights. Is it possible for us to imagine anything beyond 3 dimension? Then you are a superhuman. Congratulations.
We are like right now we're getting into 5D as well.
Sorry? We can just imagine 3D. Even for 4D means time. We do not have, right? We just can imagine 3D. But the good thing, the good news is we don't need to imagine it. It works with the same math. So, but let's get back to the book. It said, imagine that we just add one more dimension. Then it's not gonna be something like a slope. My prof told me a nice example for this. He said, it doesn't really matter that you find precise way to get to a global minimal. They said it's like a drunk person on top of a hill who goes to left and right and finally finds the lowest part of the hill. That's actually what happens. So you remember that I said we go this side of extreme, half of the, we go the other side, half it, the other side, half it, but smaller. This is how we can just control it. Does that make sense? And by saying that, there are multiple variants of a stochastic gradient descent. The momentum that we are talking about, it's like the initial energy that you give to that tennis ball. Do you want to go to a big step? That's what Prakash said. Not that big. So how can we analyze that? Technically, that's the optimizers. And one of the advantages of using Ram's prop is finding that not that big to exceed the real need. If you think of this step, it's not that much difficult actually. The momentum addresses two issues with SUV, the convergence speed and local minima. So it says that local minimum, you can avoid such issues by the momentum, enough speed for the ball, enough step size, which draws inspiration from physics. The beautiful thing is all those weights, they can chain to each other because they're all related. So you can calculate, and it is possible for computer to calculate the whole chain. By saying that, we get to where we started our sessions. You remember Hello World? We said MNIST. Now we can understand what is happening here. Guys, the good thing is that Hello World MNIST, when you load it, it goes to 4 separate train images, train labels, test images, and test labels. And then what are we going to do here, guys? We learned it today. What do we call this part? Reshaping. And instead of doing that in the video, if you had a chance to watch that video and implement the assignment 1, what did we call that? Flattening. Lovely. Excellent. And what do we call this part? Normalization, right? And is it possible to use a function for it instead of dividing by? Based on that video, and that's part of the good news is for assignment number 2, you're going to get the needed knowledge in 2-3 weeks from now, right? And you can you all have all the assignments, am I right? You have all the assignments, so whenever you think, and I think it's a good approach that you start working on it, and then when I explain, you're gonna learn them thoroughly. So what about this part? We said that we have activation value. Guys, you remember? Look at this one. Here, the activation is going to say, you know what? Forget about this one. Forget about this one. This one, half of it. This one, completely. So the activation is going to say what are the neurons in the middle should be canceled, which one of them should be intensified, and so on and so forth. Technically, here we have a picture. In the other side, we have a digit. We want to bring something totally different in texture. It's picture to something to the other side, number. So it's not a linear transition, it is a non-linear, and ReLU has that role to make it non-linear. And actually it works fine. Technically, you want to cancel the noise, negative numbers, ReLU is for that. Let's go to the next part. Now, I very much like it when I read this because now we have a better picture. Here it says, okay, can I have your attention, please, in here? Where is the knowledge? Where is the knowledge of the model? Pardon me? Is it inside input? Sorry, hidden layers. If you understand this question, sorry?
That you are providing, and on the basis of that, it's designing the hidden layer, how that thing is working.
That's the follower type. That's not the knowledgeable type. Guys, those people who receive input and they just give you the same output, do you think that they really think? Do you think that they really have knowledge? That's a very simple question. Listen to this one. What is knowledge? Means that you have a kind of a structure somewhere. Guys, exactly that is what I'm talking about, deep learning. You have a structure somewhere that you face a new problem and you can figure it out and say, aha, this is in that category. I can solve it. So what is that structure? Is it input? Input helps us to create that structure, but your input is not part of your knowledge. Training help us to create that structure. Guys, you are getting closer and closer, pretty close. During the training, what are you going to fix? Weights and biases, right? So weights and biases are there. And when you fix it, the model is already prepared. You give a new input, Malith, and it gives you the correct answer. What is it? Weights and biases. The knowledge is in weight and biases. That is what you create during training. At the beginning, like a baby has no knowledge about anything hot, right? After touching the first hot stuff, it's going to say, oh, I'm not going to touch anything like that anymore. I build that weight and biases, those weights and biases. Yes?
It's more like inputs where when like.
No.
Because.
Where are the weights? Tell me, is it input? Where is it here?
The information, like, network takes it.
Okay. The first information that you receive here, that's the cat, right? Hopefully. You're gonna say, is it cat or dog? Do you have any knowledge in here yet? We started random. Do you consider random weights and random biases as knowledge?
I think that this particular information is giving it wrong, and that's knowledge is hidden. Knowledge.
I don't know if I'm too old to have discussion about this or too tired today, but is it possible that we postpone it to another time? But I can just tell you one thing. At the beginning, we don't have correct weights and biases. Inputs help us to build up our weights and biases the way that we can just say, this picture is cat, this picture is dog. That is not because of the input, because input changes. That's not because of the output, because the classes are fixed. This is because of what we learned in weights and biases during the time, based on hundreds and thousands of examples that we saw. So we built that logic in our brain, in our weights and biases. Does that make sense? Hopefully. We are gonna talk, honestly. Next week we are gonna talk.
And this,
Yeah.
Wouldn't biases be the main source for the information, for knowledge for the program to learn?
Weights and biases, not only one. What are the parameters?
Because biases, like what understanding bias is like it shows a difference between different ways. So it can be that, am I not?
Biases are there to lift up or suppress one column's importance.
Like weights.
Weights are just a linkage between neurons, not the entire, they are individual kind of things. Okay, we're gonna talk. Let's just go to the next part. Look at this one. It says that weight tensors, which are attributes of the layers, I should underline every single part of this. That's why I made it hidden and ask you the question. Are where the knowledge of the network persists? And I very much like to ask that question. And guess what? Most of the people, they say neurons, hidden layers. They say everything but weights and biases. And intentionally, I never say only weight or biases. I always say weights and biases. That's where the knowledge persists. Look at this one. What are we going to do here? We just find appropriate function to find the steps to correct our errors. What is that? Pardon me? What is the function? Optimizer. Optimizer is the one who's going to correct correct weights and biases, the steps. Who is responsible to calculate the loss, William? Loss function, right? And what is the matrix that you use for calculating if it is correct or not? Accuracy. But what if the what do we call it? The number of classes are not balancedly. For instance, we have 100 cat picture, we have 10 dogs picture. Then accuracy is not the best. We need to use precision. This is not mentioned in this book, but okay. And the last thing that we have here, it says that find patterns between images and labels. What is epoch? Imagine that we have 100 pictures. What is epoch?
One batch. We create more batch.
No. Showing that 100 picture is one epoch. Batch is if you slice it into, for instance, 20 pictures. How many batches you are going to have in that epoch? Tell me. 5. 5 multiplied 20 is going to make 100, right? Imagine that your batch is 22. Again, it is going to be 5 because you're going to have 4 complete batch. The last batch is going to be something like 16, I don't know, 12, something like this, right? Okay, what is the batch? We talked about it. We have mini batch, we have individual, we have full batch, which overall number of pictures. Does that make sense? By saying that, we get to the summary, and 2 points in the summary. 2 points are the most important one. The first one is saying learning means finding a combination of model parameters. When we say parameters, guys, it means weights and biases. Learning means finding a combination of model parameters that minimizes a loss function for a given set of training data samples and their corresponding targets. So it minimizes the error. The next thing which is important here is the entire learning process is made possible by the fact that neural networks are chains of differentiable tensor operations, because you can simply run all the differentiation differentiable operations at the same time simultaneously, getting back to this picture that Stefan asked. So we are going to have, unfortunately, I have tons of these pictures. We're going to have many of these at the same time, and we can find global minimum for hundreds of thousands of weights and biases that we have. The good thing is all these processes could happen at the same time, and it was not possible before having those GPUs. That is why now the speed is acceptable. The next week, we are gonna start working on 3 major issues. So it's gonna be hands-on. Please be prepared to work on Colab if you need to just a little bit brush up the knowledge. The 3 major questions that we are gonna talk. One of them is binary classification for sentiment analysis, to say it's for IMDb ratings. You just want to say if a review is positive or not positive. It says that the 3 most common use cases of neural networks. One is binary classification for sentiment analysis. The other one is multi-class classification. And the last one is scalar regression for Reuters. Multi-class classification is for Reuters news. For instance, if a news belong to politics, sport, stock, what? So they have 46 different categories. And the last one is the Boston housing price. So we are going to start working on that. By saying this, actually, we are done with today's session. Please just wait for the attendance, and after that, I wish you the best of evening. Finish.